Counterflow heat exchangers. The relation already given for the log mean temperature difference for parallel flow heat exchanger can be used for a counterflow heat exchanger. So del T1 and del T2 are expressed as shown in the figure. Del T Lm Cf greater than del T Lm Pf. A smaller surface area, a smaller heat exchanger is needed to achieve a specified heat transfer rate in a counterflow heat exchanger. So del T for log mean temperature difference for counterflow is always greater than del T log mean temperature difference for parallel flow. Multipass and cross-flow heat exchangers use of a correction factor. The log mean temperature difference relations developed earlier is limited to parallel flow and counterflow heat exchangers only. To simplify the analysis of cross-flow and multipass shell and tube heat exchanger, it is convenient to express the log mean temperature difference relation as del T Lm is equal to F del T Lm Cf. Equation 26, where F is the correction factor and del T Lm Cf counterflow is the log mean temperature for counterflow gas. F charts for common shell and tube and cross-flow heat exchangers. Shell and tube heat exchanger, these two. Number A, 1 shell pass and 2, 4, 6, etc. Any multiple of 2 tube passes. Number B, the 2 shell passes and 4, 8, 12, etc. Any multiple of 4 tube passes. These two are cross-flow heat exchangers. Number C, single pass cross-flow with both fluids unmixed. Number D, single pass cross-flow with one fluid mixed and the other unmixed. There comes the next problem. Steam in the condenser of a steam power plant is to be condensed at a temperature of 50 degrees Celsius. And for this, HFG is equal to 2305 kg per kilojoule per kg. With cooling water, Cp is equal to 4180 joule per kg degree Celsius from a nearby lake, which enters the tubes of the condenser at 18 degrees Celsius and leaves at 27 degrees Celsius. The surface area of the tubes is 58 meters square and the overall heat transfer coefficient is 2400 watt per meter square degree Celsius. You have to determine the mass flow rate of the cooling water needed and the rate of condensation of the steam in the condenser. So there is a figure of the given data from this question. Steam 50 degrees Celsius, water 18 degrees Celsius and leaves at 27 degrees Celsius. So there is the solution of this particular problem. From given data we can write del T1 is equal to TH in minus TC out is equal to 50 degrees Celsius minus 27 degrees Celsius. That means 23 degrees Celsius. And del T2 is equal to TH out minus TC in is equal to 50 degrees Celsius minus 18 degrees Celsius. That means 32 degrees Celsius. So del T Lm, it means log mean temperature difference, we can write del T1 minus del T2 divided by ln del T1 divided by ln T2 del T2. So we have all this value 23 minus 32 divided by ln 23 divided by 32, and the value of del T Lm is 27.3 degrees Celsius. Then the heat transfer rate in the condenser becomes Q dot is equal to U as del T Lm. The value of U is 2400 watt per meter square degree Celsius, as 58 meter square, and del T Lm is 27.3 degrees Celsius. So the value of Q dot is 3800 kilowatt. The mass flow rate of the cooling water and the rate of condensation of steam are determined from this equation. Q dot is equal to m dot Cp into T out minus T in for cooling water. M dot cooling water is Q dot divided by Cp, T out minus T in is equal to Q dot means 3800 kilojoule per second, Cp means 4.18 kilojoule per kg degree Celsius, and T out minus Tn is equal to 27 degrees Celsius minus 18 degrees Celsius. So the value of m dot cooling water is 101 kilogram per second. Next, Q dot is equal to m dot is Fg, steam. So m dot steam is equal to Q dot divided by Hfg. The value of Q dot is 3800 kilojoule per second and Hfg is 2305 kilojoule per kg. So the value of Q dot is, value of m dot steam is 1.65 kg per second. So we have the value of mass flow rate for cooling water and mass flow rate for steam.